Alright, today's lecture is going to cover basic circuit theory. Very, very basic. We'll carry on with this when we get to the mechatronics courses as well. But for us, today we're going to cover really, how current, voltage, and resistance all work together. And we apply Ohm's law, and then we do a Kirchhoff's voltage law and a Kirchhoff's current law, and we have to see when those apply and when those don't apply. Alright, so that's what we're going to be covering in here. We're going to solve a very basic series circuit, and we're going to solve a very basic parallel circuit when we do this. But we have to understand the three basic fundamentals of electricity: voltage, current, and resistance. And there is a very specific relationship how those all connect to one another and how one influences the other and those type of things. The first, we have to revisit what current is. Okay, current's the flow of electrons or flow of electrical charge through a circuit. Alright, so when we talked about electron theory and we talked about, copper and gold and silver and how well they conduct, we're talking about that electron that's floating around there in that outer orbit. Okay, we make electrons flow. That's what current is. Okay, so current is measured in amps. We've covered that when we did our SI prefix and those sort of nomenclatures. So we call it amps when we current. So we have milliamps, microamps, amps, and we use a capital A to define that. All right. Voltage is force. That's the force it takes to make those electrons move. So for us, we measure it in volts, and you have a 9-volt battery, a 12-volt battery. That's DC stuff. There's also AC. When you plug into your house, you have 120 volts that's sending the current through and pushing it through that way. And last, we have resistance. Resistance, we've talked about this in the components piece. Resistance is what doesn't allow current to flow. Okay, it restricts the flow of current, or we can control the flow of current with a resistor. Alright, so best bet when you're at your house, alright, think about taking a hose, turning the water on, where the water represents current. Alright, you have your force, those are the different water levels, like that, how much they let the water flow out of your house is called bailing water. But as far as what it's going through, the flow that it's coming out of the faucet, and then you come along and kink the hose. You're the resistance, or you squeeze the hose so not as much water can flow out. So that's really what it is. Okay, so that's the best analogy when you turn on your hose. You have your voltage, which is your faucet essentially. Alright, your current, which equates to water flowing out of the hose, and then resistance is you squeezing it, or if you have one of those handles on the end, right? That completely stops, and then you start to squeeze the trigger on that handle, and then water will start to squirt out of it. So same kind of concept there. Alright, let's take a look at something basic here. Alright, a couple different things we need to pay attention to in this diagram here. Alright, obviously we all know what a flashlight is. And the flashlight's probably the most basic circuit we can get. So there's a couple different diagrams we look at with a flashlight. The first one's a block diagram where we actually see the physical components of what's going on there. We have a switch. Alright, we see the coil on the back of the flashlight. We have a battery. It's a D-cell battery. Alright, and then we have the light bulb, and we have the physical flashlight itself. So that's our block diagram. For you and I, as we get farther into this class, we are going to look at the schematic diagram. So take a look and go back and forth between the block diagram and the schematic diagram and see how they relate. So when we draw a schematic, alright, at the top we have a switch. Alright, that switch is what turns the power on or off. It makes the connection so that the electrons can flow and turn on the light. So we have a battery down there. That's the symbol for a DC battery. Okay, 2 long ticks, 2 short ticks, and the long ticks are positive, the short ticks are negative. Alright, and then we have the light bulb. So basically understanding a basic schematic, and we're going to start solving schematics here shortly. So what really happens with that flashlight? There's 2 pictures here. Okay, One, on the right hand side, that's before you turn the switch on. That's what the circuit looks like in the flashlight. Alright, it's wide open. There's no chance for electrons to flow because they don't have a path to flow. So it's very important that current has to have a complete path. If current does not have a complete path, current cannot flow. So we say in that case resistance is infinite, and that's important later on when we start using a multimeter to troubleshoot. In the picture on the left, or the schematic on the left, alright, we have the switch is now closed and current is flowing. When current flows and it has a complete path, those electrons turn on the light bulb. Alright, so this is called a closed circuit. The picture on the right obviously is called an open circuit because the switch is open. So, multiple things that we get out of this. The circuit closes, we're turning on the light, and heat is produced. Okay, that's the offset. You're going to learn that energy can neither be created nor destroyed, just transforms forms. The same kind of concept they're going to talk to you about. Physics, okay, is right here. So, there's two different ways that we talk about that current flows. The most common way that we use and how we do the calculations is called the conventional current. We always do this with our flow calculations and everything. It's because they didn't discover the way electrons actually flowed until they got the electron microscope. And so up until the 50s and 60s or so, in the 1950s, 1960s, we did everything with conventional current flow. And there's nothing wrong with it. It's just a polarity change. Conventional current flow means that we are saying that current flows from positive to negative when we make that connection. In reality, we have what is called electron flow. So in reality, what's happening when we complete that circuit, electrons flow from negative to positive. Okay, so that's really the difference between the two. Every single calculation is the same. The most common way we always determine it is positive to negative, but in reality, electrons really flow with and the electron flow from negative to positive. So that's why when you're jumping a car battery, you always put negative on last, because that's what the electrons are flowing through so that you don't hurt yourself. Alright, so engineering versus science. Okay, science is more an electron flow. We, engineering, use the conventional method. You will get all the exact same answers, except for just the polarity is the opposite direction. So really, that part is really insignificant when it comes down to it. The most defining law that we will ever learn in electronics, electricity, those sort of things, is Ohm's law. It's the relationship between current, voltage, and resistance. You need to know this one like the back of your hand. It's three different variables. The I is for current, V is for voltage, R is for resistance. And we've covered that before. So hopefully this stuff may be starting to click now. Some wheels are turning as we go through and take a look at this. So write that equation down. I equals V over R. You should be able to see that equation and solve for V and solve for R. So you're going to have to make sure that you know your algebraic manipulation to do that, because I'm going to give you kind of a simple schematic, a couple resistors, battery, and I need you to find some things. I'm going to teach you how to do that. Alright, the next slide we're going to take a look at shows you kind of a shortcut method. Some people like this one. It's kind of how they remember it. If we want to solve for current, alright, we draw a triangle here, and we put V on top and I and R on the bottom. Always draw if you're going to use this method, always draw it this way. You can use a circle if you want and make half of a top of a circle and 2/4 pieces on the bottom. But if you're going to use a triangle, V is always on top, and then V equals IR. That's how I actually remember it, as V equals IR, but it's whatever you need to. Alright, so if you use the triangle, and we're solving for I, so you point to I, and it tells you that it's voltage over resistance. And you know that the unit is amps for current. If you look at the middle picture, alright, and you point to R, it means you're solving for R. R is voltage divided by current, or V over I, and R's unit is ohms. Lastly, if we want to find voltage, it's the bottom triangle, voltage, so you point to the V. V equals I times R. Okay, and the unit of voltage is volts. So you should be able to do that with basic algebra that you've already learned in like 6th or 7th grade. However, if you need this shortcut, it's okay to draw this, write it down, and apply it. You need to know all 3 versions of this in this class and the next few classes that you're in with me. Okay, let's go back to that flashlight example. We have a flashlight here. It has a 6-volt battery, and it has a bulb that has a resistance of 150 ohms. When it's off, nothing's going on. But when the flashlight's on, how much current will be drawn from the battery? Alright, so remember, voltage is that force. Resistance, we're controlling how much current's allowed to flow. So, think back to Ohm's law. What are we solving for? V, R, or I? If you said I, that's correct. We're solving for current. So we got to go back to Ohm's law. How do we find current? Well, if you forgot, we flip back aside. Current, right there, current is voltage divided by resistance. And we're in our base units of 6 volts and 150 ohms. It would be different if we had kilo ohms or kilovolts or things like that. Alright, so current is going to be resistance over voltage. So write that out. Say I equals V over R. And then substitute in the values of V, substitute in the values of R. Then get out your calculator and take 6 divided by 150. You will get 0.04 amps. If you remember from a previous lecture, we don't like to say things are 0.04 amps. So we got to convert that to a nice SI unit. So we move the decimal places 3 places to the right. So that becomes 40 milliamps. Remember, when we're doing engineering stuff, we have to move the decimal place always in chunks of 3, moving it 3 to the left or 3 to the right. Okay, this one I wanted to move it to the right. Okay, so I got a number greater than 1, so that means I had to do like milli. Okay, so the current going through this flashlight, 40 milliamps. Not a whole lot. Okay, it doesn't need to be a whole lot. It might hurt a little, but even if you were to touch that, it wouldn't be, I mean, the most exciting thing in the world. It's not like you're going to get a big shock out of that, but current is the most dangerous thing. Alright, current is what kills you because it goes through your body. It will actually, when you get electrocuted or something like that, or you touch electricity, current uses your veins like wires to go through your body, and when you get hit and electrocute yourself, usually it gets to your heart. Alright, and goes through your heart, and your heart can't take it. So you always got to be very careful with current. So let's take a look at the couple of different ways that current can flow, and what the difference is between we have what we call a series circuit or parallel circuit. Now, I can deceive you with all kinds of pictures in these as well, but what you need to understand is a series circuit, the components are end to end, and there is only a single path for the current to flow through a series circuit. So you will always have one current, and the current will be the same through each element there, or each resistor when you see it. So that's on the left hand side. What we're going to call components there, let's just roll with them being resistors for right now, and that's how we're going to solve these. On the right hand side we have parallel circuits. Okay, with parallel circuits, both ends are connected to the same node. Both ends are connected to the same node, and there's multiple paths for current to flow. So in the picture on the right hand side, there's 1, 2, 3, 4 different paths for current to flow through. Alright, so that current's going to break up. Does it break up evenly? No, not all the time. Only if all those values of resistors are the same, then the current will break up equally. If the value of the resistors are not the same, the current in each branch is going to be different. Okay, so parallel circuit, there's multiple paths for current, one voltage. For series circuits, one path for current, multiple voltage drops. And we're going to get into that. I know that's another term I'm throwing at you. We're going to get there here in a few minutes when we start solving some circuits. So we're going to take a basic series circuit first. So this is a series circuit. So the resistors identify just different components we might have that's doing something. So what you need to know are all of these characteristics about a series circuit. You need to know that the current flowing through every series component is equal. So the current that flows through R1, the current that flows through R2, and the current that flows through R3 is all the same current. So if it's 5 amps, everybody's getting 5 amps there. Alright? Think of everybody just standing in a circle holding hands. That's what a series circuit is. Alright? The total resistance in a series circuit only. Some people get this confused. The total resistance in a series circuit only is we add up all the resistors. So we take R1 plus R2 plus R3 and we get the total resistance. That only works for series circuits. Please write that in your notes because it's completely different for parallel circuits. Then what you need to know for a series circuit only is the sum of all the voltage drops are equal to the total applied voltage. So what does that mean? VR1, that's the voltage drop across resistor 1. VR2, that's the voltage drop across resistor 2. And VR3 is the voltage drop across resistor 3. You have to use Ohm's law in each one of those scenarios for this particular circuit to calculate that. And then once you know all of those voltage drops, you add them up. They better equal 12. If you get more than 12, you did something wrong because you can never have more voltage than what you started with. If you get less than 12, you did something wrong because you cannot have any less voltage than what you started with because it has to be a closed circuit. So, 3 characteristics of a series circuit. The current through each element is the same, 1 total current. The total resistance, I have to add up the individual resistors, and the total voltage drops across each resistor have to equal the total voltage. Okay? So let's do some examples here as we go through this. We have a series circuit here. How do I know they're series, right? It looks like they're all, one component only touches one end of the other component. So R1 and R2 only touch in one place. R2 and R3 only touch in one place. R3 and the battery only touch in one place. R1 and the battery only touch in one place. That's how I know it's series. Okay, there's only one connection between each element here. If there was multiple connections between each element, then we would be in parallel. Alright, the current flowing through each one of these, IT, is the same. Alright, and we're going to use Kirchhoff's voltage law. That's what we just discussed what it was. Okay, we didn't give it the formal name, but Kirchhoff's voltage law is the sum of the individual voltage drops have to equal the total applied voltage. Alright, so let's work through this one. If we take a look here, okay, the total resistance for the series circuit in this case is R1 plus R2 plus R3. So this is the same circuit diagram. So what I want you to make sure that you do is have this circuit diagram drawn out on your notes. So if you have to pause the video to do it, it's the same one we've used in the past couple of slides. So draw it out exactly and label it exactly as you see it. Okay? So we're going to use R1 plus R2 plus R3. So then we just take those. Alright, 220 plus 470 plus 1.2 kiloohms. Please remember that 1.2 kiloohms is 1200 ohms. You need to put everything in its base unit. So don't say 220 plus 470 plus 1.2. You will be wrong. You need to do 220 plus 470 plus 1200. That's where you get 1890, and then we take that 1890 and put it back into SI. So we can move the decimal place 3 places to the right, and it becomes kiloohms. So that is the total resistance of that circuit. Now, we want to find the current in that circuit. We revert to Ohm's law. Total current is voltage divided by resistance. So in this case, we have an applied voltage of 12 volts. That 12 volts gets divided by the 1.89 kiloohms. Once again, take 12 and divide it by 1890. Make sure when you do calculations, put everything in its base unit. Alright? That's what I like to do, and then we put it into a nice manageable SI unit after that. We end up with, you should get 0.006349, and then we convert that by moving the decimal places 3 places to get 6.349 milliamps. So the total current in this circuit is 6.349 milliamps. The last thing we need to do is calculate each individual voltage drop. Please remember, Kirchhoff's voltage law says that the sum of the voltage drops have to equal the total applied voltage. So for each resistor in series, we have to use Ohm's law and calculate the voltage drop. Don't just write these down when you're taking notes. I want you to have your calculator out, and I want you to do this calculation so that you know that you're pressing the buttons correctly and getting the right answer. Okay? So, we know the total current through the circuit, and we know the value of the resistor. So the voltage drop at R1 is going to be the total current through R1 times the resistance value of R1. We know the total current is 6.349 milliamps. Don't use that number in your calculator. You need to put that into amps. So you have to move the decimal place 3 places to the left. So 0.006349 amps times 220 ohms. That's going to give you 1.397 volts. Now we have to take the voltage drop across resistor 2. Same current, 6.349 milliamps. Make sure you're using amps, so 0.006349. This time we're going to take that and multiply it by 470. So that times 470 is 2.98 volts. Last, we have to calculate the voltage drop across V3 or R3. I'm sorry, we're calculating V3. So total current, still the same, 0.006349 amps times 1200 ohms. I changed that 1.2 kilo ohms to ohms. So 0.006349 times 1200 gives us 7.619 volts. So, in theory, right, we should be really, really close to 12 volts when we add up the sum of the voltage drops. So there's 3 voltage drops we just calculated, 1.397, 2.984, and 7.619. We need to add the 3 of those up, and that will verify that we did things correctly using Kirchhoff's voltage law. So the sum of the voltage drops is equal to 12. 1.397 plus 2.984 plus 7.619 is approximately equal to 12 volts. So we verified that our solutions are all correct based on Kirchhoff's voltage law. So KVL for short. So if I ask you to prove that your answers are correct using KVL, that's what you would do. Calculate all the different voltage drops and then add them together to prove to me that you did your calculations correctly. Alright, getting on to parallel circuits. These guys are relatively just as easy as series circuit, but everybody gets them commonly mistaken back and forth. So please understand, when we do parallel circuits, the biggest thing that really changes for everybody is not remembering how to calculate parallel resistance. Okay? The characteristics we talked about before, this time there's multiple branches for current to flow through. Alright, there's a branch through R1, a branch through R2, and a branch through R3. We call those branch currents. Okay? Similarly, how we had Kirchhoff's voltage law, KVL, we have Kirchhoff's current law. What does that mean? It means the sum of the individual branch currents equal the total current. So the current I1, current I2, and current I3, when we add those up, they have to equal IT. Alright, but let's go back to resistance here. It looks maybe confusing to you on the slide here. I have 1 over RT equals 1 over R1 plus 1 over R2 plus 1 over R3. Okay, that's not fun to solve. You got to solve that for R1. When we do that, we get 1 divided by 1 over R1 plus 1 over R2 plus 1 over R3. That's going to get hefty in doing your algebra and making sure you're keeping all your rules straight and that sort of thing. What I have is a shortcut method, and that's what's kind of circled in white right there. It says RT equals, parentheses, R1 inverse plus R2 inverse plus R3 inverse, all inversed. That's doing all that stuff that I went through on the left in your calculator. Okay, so if you notice, there's that x to the minus 1 button on your calculator. This is where you use that. And you must put things in parentheses how you see it. So you must type it in exactly as I have it here, and you will get the total resistance for a parallel circuit. Okay, rule of thumb. Okay, the total resistance in a parallel circuit has to be smaller than the smallest resistor in parallel. The total parallel resistance has to be smaller than the smallest resistor in parallel. So if we find the parallel resistance of this circuit, it has to be less than 470 ohms. 470 ohms is the smallest resistor in this parallel connection. Notice that we have R2, it's 2.2K. Don't get that confused, that's really 2200. And 3.3K is really 3300. Alright, so we got to be careful there on those. Alright, so let's go through here, and we're going to do a couple different calculations as we go through. So, taking a look, what we need to know, we have to find total resistance for circuits. We have to find the total voltage drop across each component. Now, here's a trick to parallel circuits. The voltage drop across each resistor is going to be the exact same voltage. So the voltage drop across R1 is the same as the voltage drop across R2, is the same as the voltage drop across R3. So when we have a parallel circuit, the voltage drop across all the elements is the same. It will be 15 volts here. Very, very, very important. That's something I'm always going to ask you to solve, whether you're at this level or you're into the mechatronics level. Okay, you need to retain this. And we were going to be doing multiple circuits on this, not just in this class, but in the next couple classes that you have with me. Alright, and then we're going to use Kirchhoff's current law, the KCL, to calculate and make sure that we calculated all the parallel currents correctly. Alright, so let's do this example here. I don't have it in slideshow mode, so you're going to see it all at once, and I'll walk through it. So the first thing that I like to do, as long as we have all the resistor values in a parallel circuit, is find the total resistance. Now on the left hand side, I've given you the old school method-ish, if you want to call it that way. We have 1 over R1 plus 1 over R2 plus 1 over R3. All that solved out, and you get approximately 346.59 ohms. Or on the right hand side, I've shown you the other way to use your calculator. 470 inverse plus 2200 inverse plus 3300 inverse, all inversed. Make sure you're using that inverse button on your calculator. Alright, that x to the minus 1. So that's how you get the total resistance. You're going to get 346 ohms approximately. Okay, and then we know the voltage drop across each one of these is 15. What do we have to find next? The individual branch currents. This is where you must apply Ohm's law. So make sure that you are always noting in your head, I know I need to apply Ohm's law. If you did a circuit and solved a circuit here without using Ohm's law, you didn't do something right, because you need to apply it. Alright, so let's take a look at this. You can see on the screen in the upper right hand part of the schematic there that I now show all the different branch currents, I1, I2, I3. Each one of those currents is dependent upon the resistor value. Okay, because remember, resistors do what? They limit the flow of current. Even though each one of those resistors have the same voltage across them, they're going to have different currents because they're different size resistance. So we have to use Ohm's law in I equals V over R, and we're going to do it for each individual R. Do not use R total here for the branch currents. Alright, so make sure you have your calculator and make sure that you get these values when you type them in. Alright, so I1 is going to be V1, or V across R1, divided by R1. So 15 volts, because that's the battery that's on there, divided by 470. You're going to get 0.031915. We have to put that in engineering notation for our SI prefix, so we're going to move the decimal 3 places to the right and get 31.915 milliamps. The current through resistor 2 is voltage divided by R2 now. So we're going to take 15 divided by 2200. Okay? 2.2K is 2200. So 15 divided by 2200 is going to give you 0.006818. And then we move the decimal 3 places to the right, and we get 6.818 milliamps. I3 is 15 volts divided by 3300. That's going to give you 0.004545. And move the decimal place 3 points to the right, and we get 4.545 milliamps. Now we've calculated all 3 branch currents. If you had a 4th resistor on there, you would have to find that 4th current. So however many resistors are in parallel, that's how many different currents that you have to find. So in this case, we have to use Kirchhoff's current law. Okay, we're going to check all those out. We're going to add the 31.915 milliamps plus 6.181 milliamps plus 4.545 milliamps. And we need to see if that equals what the total current is. Well, to find the total current, we have to take the total voltage divided by the total resistance. This is the one time you use the total resistance to do this. Alright, so when you do that, we're going to take 15 divided by 346. Okay, you're going to get 0.043278. Move the decimal 3 places to the right, and you get 43.27 milliamps. So, in order to check Kirchhoff's current law, we need to add up those individual currents. And 31.95 milliamps plus 6.818 milliamps plus 4.545 milliamps does indeed equal 43.278. If your numbers aren't exact, it's okay. It just depends on how many decimal places you use it. Alright, so if you're in the high 42s, low 43s, and you're in that ballpark, you're completely fine. If you're at 35, you're not fine. You did something wrong. But if your number isn't exact decimal for decimal, that's fine. But as long as it's close enough to 43, yes, you did do it correctly. Alright, so that's Kirchhoff's current law, or KCL. The sum of the branch currents have to equal the total current. So, just to reiterate, Kirchhoff's voltage law, or our KVL, we apply that to series circuits only. Make sure you put that in your notes. Kirchhoff's voltage law is series circuits only, and its sum of all the individual voltage drops have to equal the total applied voltage. And remember, how did we find the individual voltage drops? We had to use Ohm's law. Okay, so V equals I times R in that case, and found each one of the voltage drops and had to add them up. They had to equal the total battery voltage there. Okay, Kirchhoff's current law, that's the total current in the parallel circuit, has to equal the sum of the individual branch currents. So all those branch currents added together have to equal the total current of the circuit. Kirchhoff's current law only applies to parallel circuits. So make sure that that's in your notes. So KCL is only on parallel circuits. KVL, Kirchhoff's voltage law, only applies to series circuits. Alright, when you're done with this, go ahead and take your lecture quiz.